In this video, we present high-level control and perception for modular reconfigurable robots. This project is a collaboration between Professor Mark Yim's group at the University of Pennsylvania, Professor Hadas Kreskazit's group at Cornell, and Professor Mark Campbell's group, also at Cornell. Modular robots are systems composed of simple repeated modules that can be combined to achieve complex tasks, and reconfigured to form many configurations. Our goal in this project is to take high-level task specifications and distill them down into concrete solutions to problems using modular robots. To begin, we present S'mores V2, a new modular robot developed at the University of Pennsylvania. Like version 1, each module has 4 degrees of freedom: pan, tilt, and left and right wheels. Each module has its own battery and communicates with a central computer over 802.11 Wi-Fi. The modules connect to one another using 4 electropermanent magnets on each face. EP magnets consist of an electromagnet coil wrapped around 2 permanent magnets, and can be turned on and off by sending a pulse of current through the coil. Once activated, they sustain a holding force of 20 newtons per magnet with no constant power consumption. They only require power when switching states. So far, we've built 8 S'mores modules. In total, we plan to build 30. This video shows a simulation of 30 modules moving and reconfiguring. We are also developing a sensor module featuring 2 Intel RealSense RGBD cameras and an Odroid Linux CPU. The module will be self-contained and attached via magnets to a S'mores cluster, allowing the environment to be sensed and mapped. The advantage of modular robot systems lies in their flexibility, the ability to assume different shapes to provide different functions. However, this places an additional burden on the user, because addressing a new task requires them to configure the hardware appropriately. Likewise, programming a new hardware configuration is time-consuming, since primitive behaviors must be developed and debugged before complex tasks can even be attempted. At ISRR 2015, we presented an object-oriented design framework for modular robots that lets users create configurations and behaviors by composing elements of a design library, and provides tools to verify and simulate their creations to ensure they will work properly on the hardware.
Here, we show an example of how we can create a 4-legged walking robot. Using a graphical user interface, we select subconfigurations from a library and specify how they should be connected. With a few clicks, we compose library elements to act as a body and 4 legs, and then review the final design. At this point, the configuration is automatically verified for self-collision and gravitational stability. For instance, if we had made a mistake and created an unstable design, as shown here, we would receive a warning. Once the design is verified, we can create a walking behavior. Since the walkbot is composed of sub-configurations from the library, we have access to all the behaviors associated with them. We compose behaviors in parallel to make 2 legs move simultaneously, and then in series to make the walkbot take repeated steps. Behaviors are represented as series parallel action graphs. In the bottom right portion of the screen, we can see the graph grow as we create the behavior. When the behavior is finished, it is automatically verified. The walking behavior we just created is good to go, but if we had made a mistake and caused 2 legs to collide, we would be alerted automatically, as shown here. These automatic warnings save us time. Without them, we would not find the bug until we simulated the behavior. This can take a lot of time, especially for complex configurations and behaviors. Once our configuration and behavior pass verification, we are ready to simulate. Simulation serves as a final check that the configuration and behavior perform as expected.
So far, we have built a small, hierarchically organized design library. We intend to grow this library into a standard library for the S'mores robot, analogous to the standard libraries for object-oriented programming languages. We hope this will serve as a valuable tool to users approaching new problems. In the near future, we plan to create a large library of designs and behaviors through crowdsourcing. Researchers at Cornell have created a design tool called VSpark, which is freely available online. Users can create new designs and behaviors for S'mores and test them out in simulated environments. When a user has created something they like, they can save their work to a web server, where the creation becomes instantly available to everyone else using the app. In this way, we hope to create an ecosystem of useful designs and behaviors. This work was funded by the National Science Foundation. Thank you for watching.